In this tutorial, we discuss the breadth first search, aptly called as BFS algorithm. And we will, if we recall, DFS algorithm takes the traverser a long way from the home, and it grows, the DFS tree grows in a depth-wise fashion, while BFS is said to be tuned for cautious people, because as it visits vertex one by one, it proceeds in a concentric manner. By visiting first all the vertices that are adjacent to the starting vertex, and then all unvisited vertices 2 edges apart from it, and so on, until all the vertices in the same connected component of the graph is visited. And by then, if there are some vertices which still remain unvisited, the algorithm has to be restarted at an arbitrary vertex of another connected component of the graph. And we will just proceed step by step with at least 2 examples, so that we will consolidate idea about the famous algorithm BFS. It proceeds in a concentric manner, I told you earlier, by first visiting all the vertices adjacent to the starting vertex. Then it visits all the vertices that are unvisited, 2 edges apart. This is a very important point to remember. It continues doing so until all the vertices in the same connected component as the starting vertex are visited. If still unvisited vertices remain, the algorithm will restart at an arbitrary vertex of another component of the graph. And we will take this example here, and the algorithm implements Q. Okay, while this demarcates DFS from BFS. While DFS implements a stack, BFS implements a queue. Okay, it starts with the starting vertex, that is like DFS. BFS will also choose the vertex of higher alphabetical order. So in this case it is A. So it visits A and marks for having visited, and it inserts, it enqueues A into the queue. Okay, the queue length will be naturally equal to the number of vertices present in the graph. So there are 8 vertices over here, 8 vertices. There should be 8 cells in the array, 8 cells in the queue, rather in the queue. Okay, it is 4 plus 6, right? 8 vertices, 8 cells will be present. So A is visited and A is enqueued into this queue. So this is the first one to go into the queue. And the algorithm looks around for directly connected vertices. For this, B is directly connected, E is directly connected, and B and E are therefore the immediate vertices or immediate neighbors. So it visits B and marks for having visited, then it inserts into the queue, that is, it enqueues B. So B is the second vertex to go to the queue, and of course you should remember the entry into the queue will be from rear side, and the exit out of this queue will be from the front side. Okay, that is known to us. Okay, and next vertex is E. Okay, because A is also attached to, E is attached to A, B is attached to A. B is chosen first because B is of the higher alphabetical order. So this is E3. Now from A, all the vertices which are directly connected as exhausted. Therefore A will be removed, A will be dequeued. Now the algorithm jumps to B and it will connect whatever the vertices that are directly connected to B, and it inserts. So C is connected to B, okay, therefore C will be entered into the queue, or C will be enqueued, and C is the fourth one. C is the fourth one to go to the Q. Yeah, and the other vertex is F. F is also NQ'd. So this is F. This is F. And you should recall over here. You have to notice a very important point over here. After A, it is C. Therefore, as the algorithm progresses, by looking into another vertex, the next vertex, it will have jumped 2 edges, number 1, number 2. So it has come to C. While coming to C, it will have crossed 2 edges. So from C is over now, okay. The connected vertex is at B is over, therefore B will be removed from the Q. Then the algorithm visits C. Sitting at C, the algorithm covers D as well as G. So D as well as G, because they are directly connected to C. Now B is removed anyway. So here D is the 6th vertex to be NQ'd, and G is the 7th vertex to be NQ'd. Then at C, everything is exhausted. All the directly connected vertices are exhausted. Therefore, the algorithm jumps to C, to D. And at D, it connects only to H, because that is the only vertex that remains. So H is inserted into the Q. Okay, H is inserted into the Q as the 8th vertex, and E will be DQ'd, then C4 will be DQ'd, F5 is DQ'd, D6 is DQ'd, G7 is DQ'd, and H8 is DQ'd. Okay, this is how it moves. And this is, as you might have guessed, it is called as BFS tree. This is BFS tree. Yeah, BFS tree. And this is BFS Q. This is BFS Q. And you should notice, like DFS tree, there are tree edges. Okay, these are tree edges. Tree edges will represent the way in which the algorithm progressed vertex by vertex. They are called as tree edges. And you can connect H and G maybe by dotted line, because that was not the traversal way, but anyway it is connected. And G and F is also connected. And how does the algorithm come to know that G and F are connected? Okay, because algorithm moves along with adjacency matrix also. Adjacency matrix will give a clue as to what are the vertices which are mutually connected. Now, these dotted lines are called as cross edges. Okay, cross edges is to BFS, and back edges is to DFS. The presence of back edges represents the presence of a cycle in a graph, and presence of cross edges will represent presence of cycles in a graph. So using these dotted lines we can make a circuit, and so also over the graph A, B, C, D, E, H, G, F, E, A. And similarly here also there are local cycles over here. There are local loops over here covering only few of the vertices A, B, F, E, A, B, C, G, F, B, C, D, H, G, C, something like this. Okay, so we have demarcated difference between BFS and DFS. But with BFS it is not possible to represent the articulation point, but anyway BFS for graphs of this kind it will give minimum edge path between any two vertices selected at random. For example, A to E, this is the only one path which is the minimum, and if this graph were to come along with the weights, this is the minimal path. And once again from to F, from A it is A to B, B to F. To C, it is A to B, B to C, something like this. Okay, this is another difference between BFS and DFS. And here, there is no question of backtracking. Once the path is decided, that's over. Once again, the algorithm will never backtrack, unlike DFS algorithm. Therefore, BFS is classified to be coming under what are called as greedy algorithms. Greedy algorithms will never backtrack. Once the decisions are taken, it is the final decision. Okay, and anyway, once the decision is taken, it will never be modified or never be revoked. Okay, we will take another example where there is a connected component. This is a graph altogether. This in its entirety, this presents a graph with several edges and several vertices. But anyway, there is a subgraph over here in a main graph. This may represent the fence of some property, or maybe outer ring road, and this may represent some of the predominant points in a city. As you recall, the problems which are graphed, maybe a weighted graph, maybe a connected graph, maybe an unconnected graph, is the translation of some kind of a practical problem. All problems cannot be graphed, and any problem that is graphed may be addressable by means of a host of available graph algorithms. And here the case in point is the traversing algorithms. These traversing algorithms, as I told my respected viewers in my previous discussion, that traversing is all about disseminating a graph or making a computer to understand a graph in order to elicit some of the important properties of the graph. And we will check up this particular graph and we will see how exactly traversing will take place. Okay, so first of all, this is the component of the graph and this is yet another component of the graph. Anyway, since they form a single graph, they are connected components. Okay, A, E, D, C, B is one component, F, I, H, G is another component. But anyway, the entire graph in its entirety will be available in the form of an adjacency matrix that is known to you, that is well known to you. So it will pick up A during its traversal. This is the first vertex to be visited by the algorithm, and A will be enqueued. And we will have an array over here of about say 5 cells or 5 elements. This is the queue, actually this is the queue that is represented. Anyway, entry of the elements will be from this side and the exit from this side. That is well known to you as a data structure. Okay, so A is entered over here because that is the first vertex that is visited by the algorithm, A1. Then B is connected to A, directly connected to A. D is connected directly to A. E is also connected directly to A. Therefore, it visits all the vertices that are directly connected to A. So it is B. That's how we say the BFS algorithm moves concentrically without going for a long distance. Therefore, it is also greedy. It's also greedy. Sitting at a common place, it will just encompass whatever that is available. So A to B, then A to D. D is also marked for having visited, and A to E. You can see a bunch of vertices getting attached to E. Had it been DFS, we would have gone for a long distance. So A is marked 1, B is marked 2. That is the second vertex to be enqueued into this queue, and this is D. D is the third party to enter into this queue, and E is another one, the next one, that is the fourth fellow enter into the queue. So all the directly connected components, directly connected vertices with A is exhausted. Therefore, A is dequeued. A is dequeued. Then algorithm visits B, and it is already marked. Okay, from B it will look around for the possible directly connected vertices, and C is present over here as a directly connected component. So C will make an entry into the queue. So this is as a fifth component. Now all the vertices in a component of the graph demarcated by A, B, C, D, E is over. You can see C and D, sorry, what is that? D and E can be connected. D and E it should be connected by dotted lines, because that was not the way when we traversed, or when the algorithm traversed. And you can see B and D may be connected. B and D may be connected. B and C is connected. C and E can also be connected by dotted line. Of course, there are 1, 2, 3 cross edges. 1, 2, 3 cross edges. Therefore, there should be presence of 3 cycles or 2 cycles. There are 2 cross edges. Sorry, A, B, C, E, A. I repeat, A, B, C, E, A. One loop. Then A, D, E, A. A, D, E, A. Okay, so there is one loop over here, a bigger loop covering all the vertices, and there is a smaller local loop covering only 2 vertices. Therefore, cross edges, presence of cross edges in the BFS tree will simply indicate. Okay, of course, it's going to be BFS forest. You will shortly see that how exactly BFS forest would emanate. Okay, right, but the graph is not completely traversed yet, and the algorithm, when the algorithm looks at the adjacency matrix, it finds few other vertices being marked with 0. Therefore, once again the algorithm is implemented. It will start from F. So this is gone, this is also gone, this is also gone, this is also gone. You should remember now this Q is empty. Okay, in order to avoid the overwriting, I am writing the Q yet again, but in reality it is the only one Q. Okay, of course, which is already vacated. For the sake of clarity, I am writing the Q yet again, but it is the same Q, because all these A, B, D, E, C have been already enqueued. So algorithm visits F in its second new iteration. So this is the 6th fellow enter into the queue. F is the 6th vertex to be enqueued. From F it has a direct connection to G as well as I. G is alphabetically superior. Okay, therefore it will visit G, or that is our convention, and then it visits I and marks for having visited. So F6, G7, I8. So all the directly connected vertices with F are over. Therefore F is dequeued, and it will just go to G. It will just visit G. It's already marked to be visited, and from G it will have a direct connectionality to the H. So H will be marked for having visited. So H9. So all the directly connected vertices from G are over. Therefore G is also dequeued, and there is nothing to move from I. I is also dequeued, and H is also dequeued. So this is how algorithm completes its journey or traversal. And you may notice that H and I can be connected by a dotted line. So there is one cross edge. Therefore there should be one loop, a bigger loop. F, G, H, I, F. Okay, there is a loop. Therefore BFS will also give a clue as to whether or not loops are present in the graph. So with this we will just complete writing the algorithm of BFS. That's how it goes. Okay, you should carefully follow me. Mark every vertex. What it does, it traverses, BFS algorithm traverses a graph, okay, what it does, then the input for this graph is the set of vertices and set of edges. Output of the graph is a graph G with all the vertices marked with consecutive integers for having visited. I repeat, the output of this algorithm is a graph G, the given graph, with all its vertices marked with consecutive integers for having visited. Okay, so as an initialization, every vertex in V, the set V, is marked with 0. It should not be read as O, it should be 0, marked with 0 as having not visited. Then there is a setup of a global variable called count. Count is 0 because none of the vertices have been still visited, therefore count is set to 0. For each vertex small v, lowercase v, representing any vertex that has been selected for the first time, it could be A. If the graph contains all the vertices marked with English alphabets, it should be A, capital A, let us say, or it should be 1 if the vertices are marked with 1, 2, 3, 4. Okay, so for each vertex small v, any vertex in the set V, do repeatedly. If V is marked with 0, then send this V to another algorithm, subroutine or sub-algorithm titled BFS, which will do the duty of marking the vertices that are sent to this particular function with consecutive integers. So this algorithm comes just like that, BFS V. So V is the parameter that is to be supplied to this sub-algorithm, and count will become count plus 1 because it is already visited V. So V will be marked, this V will be marked with count is 1 to start with, and initialize a Q with V. So the first vertex enters into the queue. So that it happens like that. Okay, then while the queue is not empty, do the following thing with the, okay, while the queue is not empty, each vertex, for each vertex W, some other vertex which is directly connected to V, okay, for each vertex W in V adjacent to the front vertex, that is A or small v, do. If W is marked with 0, then count will become count plus 1, it will become 2. So W, which is an adjacent vertex to V, will be marked with count, and this W will be added to the queue. Remove the front vertex from the queue, and the algorithm is repeatedly applied. I think this completes the DFS algorithm. To make a quick note of this, okay, and we can write the differences between DFS and BFS, okay. My respected viewers are supposed to note this, okay. I request them to note this, BFS, okay. This will come maybe in a selection test, etc. Okay, it uses a data structure which is nevertheless stack, while BFS uses a queue. Okay, while when the vertex enters into the DFS, it is marked with the first notation, first ordering. When it leaves, it will be marked with the second marking. Therefore every vertex after the completion of the algorithm, okay, after the algorithm makes a complete visit of all the vertices, every vertices in the stack will have been marked with double ordering scheme or two ordering scheme, double ordering scheme. The first ordering will represent, okay, which instance it entered into the stack, at what instance it left the stack, at which instance it was pushed into the stack, at what instance it was popped out from the stack. When the vertex becomes a dead end, definitely it will be popped. But here it carries only one ordering, okay, one ordering. Okay, it will represent both NQing as well as DQing. Okay, only one order. This is not a greedy algorithm. Okay, this is not a greedy algorithm, but this is a greedy algorithm. And this can be, DFS can be used to represent, to find the connectivity of the graph. Okay, connectivity, the cycles in the graph, as you have noticed. Okay, as many back edges, as many cycles, and other than this, it will also help us to find out the articulation points. Okay, all about articulation points in a graph has been discussed in our tutorial on fundamentals of algorithm analysis. Okay, maybe the 4th volume. Okay, articulation points can be found, if at all any, using DFS, and this will also can be used to check the connectivity. This can also be used to find the whether cycles or loops exist in a graph, but it cannot be used to find out if at all any articulation points are present in a graph. But anyway, BFS can be used to trace minimum edge paths from any two vertices selected at random, any two vertices chosen at random. As far as complexity is concerned, it falls under big theta of cardinality of the vertex set whole square. So it's a quadratic complexity. Cardinality is number of vertices present in the graph. Same thing, same complexity holds good even for BFS also. So it is V square. Yeah. If the graphs have been represented using adjacency matrix, if the graph were to be represented by adjacency list, then the complexity happens to be cardinality of V. It becomes linear. Cardinality of V, that is vertex set, and cardinality of edge set. Okay, same thing holds good even for BFS. Therefore, as far as complexity of the algorithm is concerned, there is a commonality between BFS and DFS. Okay, so with this we will complete the graph applications which are graph algorithms which are based on the famous decrease and conquer technique. And next we will take up topological sorting of a graph, which is yet another important application of decrease and conquer. Until then,